So what we're going to talk about today is what happens to our construction project when we decide it's time for us to go ahead and use less clinker, less energy, less embodied emissions in our concrete structures. Now, we of course have to meet our societal needs with concrete structures, whether they be shelter, water treatment, somewhere to watch a football game, whatever the purpose of the structure is. We want to do that, and I would suggest that engineers have always been doing that, using as the smallest amount of resources possible. I always remind students that an engineer is a person who can do well for $1 what any fool can do for 2. And so in some of these cases, that's true. And it would be wrong not to talk about where we have to go, and we'll cover this in a little bit more detail as well, is that the U.S. continues to lag behind Europe and Canada in changing their codes for exposure classes. This is an older ad, but things like minimum cement contents, this is the only way to design the mixes, often can cause problems. And one of the things to highlight is that a prescriptive specification often results in undesirable, unintended consequences. Now, performance-based specifications have been around for a long time. This is a cartoon that was quite popular when I was in the ready-mix business. You could tell you were a ready-mix concrete producer because you had that hat on. And this gentleman, being a very good Canadian, says, I want your concrete to pour like Niagara, have the strength of Gibraltar. It's pretty straightforward, right? We have some obstacles. We are developing new technologies and new materials. And some of those new technologies are going to require new processes and new construction methods, and some of them aren't so obvious and are going to require. We're not making this change because we don't like Portland cement. Portland cement is cheap, it's effective, it's available almost everywhere, it's somewhat predictable. We're making this change because we want to reduce emissions and reduce our energy needs, and history tells us, because the history of the development of Portland cement tells us, that we are going to encounter problems that we don't know exist right now. Of course, we've been using concrete for a very long time. The Pantheon in Rome, it's got some lightweight aggregate in here, which no doubt was done to reduce the amount of cement up here, cementitious material, hydraulic cement, and therefore reduce the carbon footprint of the structure. But for whatever reason, there's a lot of things that have been done for a long time, but we still use this device. And we will use this device for the foreseeable future. And it's been around for a while. Some of you may not have the 1929 version of the Design and Control of Concrete Mixtures, but it has the same table that you will find in ACI 211. A modern way of specifying it, because we can change that slump without changing the water, unlike 1929, is just to say, make the slump whatever is fit for the intended use, and designate a range. And then if you're in the ready-mix producer business, if you keep getting a different slump and you think you're doing the same thing in each batch, one of those two things is true. And so you need to be aware that performance-based specification is where we're going to have to go, and it's going to require a change in construction methods. And even more importantly, the use of lower emissions concretes is going to result in materials that are different from that containing high volumes of clinker, right? I see you nodding your head. Yeah, obviously, thanks. I really I miss a dinner for this. That the point being, if you don't communicate early on with the people that are going to construct the building, that are going to maintain the building, that are going to design the building, we can run into problems. It's going to necessitate more communication in terms of what is our concrete going to do, because we all know, right? We have a rule of thumb that, Portland cement, your 7-day strength is 2/3 your 28-day strength. That is true for mostly Portland cement mixes, even with a little bit of fly ash or a little bit of slag or a little bit of silica fume in them. Maybe not silica fume, but as you go along. But I'm going to show you one, and I'm going to give you some case study examples. The color of your concrete is dependent on two things: the pigment loading and the base color. This is a slide from Semstone that has a very pretty printed, just like you would get at the hardware store, a little chip that shows you the color of the paint. The salesman, by the way, told me when I said this was a bad idea that no one would ever hold this up against the concrete and take a picture. It only took 4 days. So we've had a warning on the color card that said it's going to be dependent on the base color of the concrete. It affected the color massively. And what was the problem with those colors as we went to high volume fly ash in interior concrete mixes? That they wouldn't like the color, and so what would we do? We would tear it out and do it again. So no matter how much clinker we didn't use the first time, we ended up using a lot more by doing it the second time. Plus, everybody wanted that. But that's not really why we're here. We're here for structures like this. And I've been doing low emissions concrete for a long time. This headquarters building built in Minnesota during the fall and winter of 2003 is high volume fly ash, 65% fly ash. Grey River Energy owned power plants, and some of their power plants sat in Wyoming on the Powder River Basin, where the coal is very consistent. Therefore, the fly ash was very consistent from their base loaded plants. And they said, I want this building to have as much fly ash in it as possible. And the architect called me up and said, hey, how much can we put in? Thinking, I want to go from 25 to 35. And I said, well, 65 without doing too much work, and we could probably do better than that. So we had a target for platinum LEED. It was a reduction 45% in our cement content, our ground clinker and various other things content, and we met that requirement, and the owner was very happy. The problem is that sometimes you can end up having a problem. Now, this is 20 years ago, and so of course we say, well, we'll go to 65% replacement, but you only want 45, so we'll up the cementitious material, which is not the biggest change. However, I then gave a presentation in a room much like this one, and I put up the mixture proportions, and somebody very carefully transcribed them down in writing. And then they said, now I have a recipe for making that high volume fly ash concrete. And we listed the admixtures that were used. They only changed the admixtures. Cementitious material source, same fly ash. But if you go from a polycarboxylate that has a tendency to accelerate and switch that in with a lignosulfonate, a wood-based material, it isn't quite the same. Now, when concrete doesn't set, this cannot always be seen as a problem. Non-setting concrete could be an advantage, particularly if you need to get somewhere in a hurry and someone doesn't think that's a good idea for you. And of course, in this particular case, you can imagine the kind of ticket you would get for doing this. But I'm sure that she let herself off with a warning. And then to make it worse, this next placement was done in the winter, in February. And so on day 3 of the concrete not setting, the contractor called me up. I was working in the ready-mix business at the time and said, your concrete isn't setting. And I said, what are you talking about? You used brand X for that project. Right, but they used your concrete and it's not setting. You've got to come down here and fix it. So being the engineer, right, I got to go solve the problem. I can't just tell them to go away. And so we ended up heating it up. And of course, that was simply retarded by the presence of the admixtures. Mixtures, here was one that had worked very well. The contractor was extremely happy with the way it performed. Change one little ingredient, don't do any trial batching or trial placement, and you end up with trouble. Of course, anyone notice the problem with the winter concrete? Do you see the top of the footing is already turning white, which means it's already frozen? But that's okay. Colleague of mine, Dick Staley, had to build a radiation bunker, their facility in St. Paul, for holding their nuclear density gauges. He said, what would be really cool is let's make concrete that is as environmentally unimpactful as possible. This would have been 2005. And so we made concrete that has almost nothing in it. It has 2% by mass virgin material. All the aggregates recycled, all the water's reclaimed. The only new material is a little bit of Portland cement and a very little bit of admixture. And he ran a bunch of tests for us, and we got rapid chloride permeability at about 490 coulombs passed. Setting time was reasonable because we knew what we were doing. And this was based on concretes we've been doing for mass concrete that were about 15% by mass Portland cement, about 600, about 580, I should say, total cementitious. Air content looked good, and the strength gain was fairly respectable. Out at 90 days, we're about 4,500, and these are laboratory cured cylinders. And we're going to come back to laboratory cured cylinders in a minute. The concrete looks really nice. You can see the very green-blue paste that's full of slag and the recycled aggregate paste. Some of those recycled aggregates completely stripped of paste fraction. Some of them are all paste fraction. 82 pounds of ordinary Portland cement. Everything else was recycled. All the water was reclaimed. And we were surprised. We've been doing this for mass concrete. We were surprised at the durability. And this led to us designing a bunch of concrete for a bunch of high-performance bridges that are throughout Minnesota. And so I'm going to attract your attention to just a couple of these mixes. This first one is 80 pounds of cement, 360 pounds of slag, 90 pounds of fly ash, total 530. It has 4,000 PSI laboratory cured strength at 4,000. There's another good one here. 8,000, it's specified to be 7,000 PSI at 28 days. It has a little bit of silica fume, a little bit higher cement content, and this material is used in post-tension transfer beams on the bridge that have to be pulled at an age of 2 days. So obviously, if you're only getting 6,300 PSI at 28 days, you must not be getting very much early on, and that's not the case. You were able to design the mixture that we got great performance. Now, of course, regrettably for our colleagues at the concrete placement, they found that there was an influence that would come out from time to time to strip them of productivity. This is the pontification method of attempting to explain to the finishers why the concrete looks so different. And you'll notice there's a couple people paying attention. There's one guy like, would this little guy ever shut up? All right. We did these materials in very severe weather conditions. Conventional cementitious content, similar to what you were seeing, 625 pounds per cubic yard is for precast elements. And here are some elements that are 32 foot by 16 at the base, 16 foot square in the middle, placed as mass concrete on a very exciting day in February of 2008 in Minnesota. The crews that built this structure believed they were going to be spending the winter in Southern California. There were a lot of very sad people who would often ask questions like, not how, why would anyone want to live here? And you can see that the structure went fairly well. Those of you who recognize what happens with slag will see that this mixture is full of slag. The performance was terrific. These forms had to be redone. You can see that they are hanging the forms on and getting ready to do pulling the forms, getting ready to do the twin structure on the other side. They had to strip the forms in 3 days. So they said, can we do this? And I said, well, probably not by accident. So what we did is we probably had the only mass concrete placement in history where we enclosed it and heated it up to 100 degrees for the first 2 days, so that we got it nice and warm, that we got the maturity that we needed, and we monitored this all with maturity. Had we been the ready mix producer and not on the design team and talking to the contractor every day, the contractor would have gone to the third day and said, what do you mean I can't strip my forms? It's in my schedule. Costs incur. And what happens when we incur costs? We try to make sure we find out who else or who is to blame for them. But I'll give you a less structural but more relevant problem. There's a patio that was constructed, a restaurant in Wisconsin, stamped concrete with broadcast color. The architect required a pozzolanic replacement of more than 50% fly ash, and this did not make it down anywhere further than the lab or than the plant level, where the plant said, oh yeah, we'll just pull out 300 pounds of Portland cement and we'll substitute in 300 pounds of fly ash, which immediately gives us a yield problem, so I can get the accountants interested in the problem. Then I get some real traction. The concrete was placed in October, and even if you're born to do engineering work, things can go badly. And so there was a great award ceremony in December, and the head of sales and the president of the company and everybody else went my invitation because they know how much fun I am at small talk, was intentionally missed. But I got to go to the meeting in March, because in March, if you don't cure the concrete, you are going to have scaling. And this scaling, you can get an idea of how the concrete once looked. It doesn't look like that anymore, and it had to be removed and replaced. So these type of things can cause us lots of problems. We need to try to recover all of these materials, and this is an older slide, that's why it says LEED credits, because that's how we used to think about this. It's not how. But no matter what you make your concrete out of, it needs to cure and it needs to dry. This is an exposed concrete that used to be at the entrance to the headquarters of the ready-mix company that I worked for, undergoing a little bit of attack at the joints. So I used to refer to the parking lot as a museum of defects because it was paved with loads rejected from somewhere else. The reason that we're seeing some of these problems is we can find in the literature a beautiful curve that looks like this. There's the pore, intruded pore volume for ordinary Portland cement in black, for 50% slag in red. But what they don't tell you is that one of them is measured at 3 days and one of them is measured at 28 days. And so frequently, scaling is the first indicator that we have incompatibility, similar to the setting. And to close this off, because we started with scaling, concrete beauty is only skin deep. This is the Hastings Bridge, a bridge across the Mississippi River at Hastings, Minnesota. You can see the existing structure, a steel arch truss. That steel bridges became very unpopular in Minnesota after the collapse of the one downtown, and so we took a bunch of them out and we replaced them. This is a tied arch, and it's a very pretty structure. From a structural point of view, it's really interesting because that beam, the arches and the beams that are connected were cast at the side of the river, floated out, and then jacked in place. This was probably not the headline that they were looking for that next spring. Hastings Bridge, flaking concrete, not unsafe, MnDOT says. And you can read the rest of it. The surface is scaled because the concrete that was put in place was this 80 pounds rather, of Portland cement, about a 90% replacement 95% replacement in this case. But the specification said, at 48 hours, for all balustrade walls, you remove the forms and you sack rub it. Concrete that is meant to be hydrating in a mass element at 140, 150 degrees, at 48 hours in a element that's only 8 inches wide, is not very mature. And so it scaled dramatically. And below, in about 3 millimeters, after that sacrificial layer of paste was gone, concrete was fantastic. We ended up removing all of the concrete under warranty work. I think it's a defect in the design. And replacing it with a cementitious material that is still there. In fact, they commented that some of it was flaking off, and it is flaking off where the 18-wheeler ran into it and appears to have ridden up on the balustrade wall for a little while. It's flaking off there. Other than that, it's in great shape. We have unclear responsibilities as we go into these items, and I'm not necessarily, but I am talking about things where we're putting a little bit of limestone in our cement. All these things are absolutely necessary from a sustainability, from a climate change point of view. But we're going to have performance issues, and we're going to have to change the way in which the structure is being built, which is not a problem so long as everybody knows that beforehand. Ward Malish and Bruce, when they were at ASCC, and when I was chairing the P2P committee for NRMCA, put together a document that talked about what's your concrete going to do at 70 degrees, at 45 degrees, and at 90 degrees. So you had a skeleton for having that very discussion. Because if you find out that it's set so fast that you can't get anything done, or it takes 3 days to set, that has a tendency to interfere with the schedule. And the schedule, as you know, Mike, the schedule is a suggestion. You just follow it, and if you don't, well, you didn't follow it. That's okay. The one thing I do know from teaching in construction management is that the float belongs to the general contractor. Now. So concrete is rapidly changing, and our codes and standards are not, and I would argue cannot, change as quickly. We need to reduce or eliminate clinker concrete of our concrete. Well, we can currently use high volume replacement with pozzolan. 85, 90%. I've got structures that are 2 decades old sitting in the Mississippi River without any scaling, without any freeze thaw damage. So I'm not telling you that I did it in a lab. I made it at 200 cubic yards an hour using conventional plants and conventional people. We're on the cusp of using materials that would require massive infrastructure investment, where we're going to have to use sodium hydroxide, for example. People rationally talk about caustic soda at 10 moles per liter sitting in tanks at a ready-mix plant. It's not like the bad old days where you'd wash your hands with Trichlor to get the asphalt off in a lab, and maybe it might cause cancer. That will cause loss of your skin right now. So we need to know that. And our construction and design methods are going to change as we adopt new materials. But we've done that before. This is a core, right? Good thing I told you that. It's not so much interesting. It's gap graded, proof that the tarantula curve is not new. And this structure core was removed from the port of Trajan, where it's been sitting in the Mediterranean for a couple of thousand years. Looks like conventional concrete to me. There's no Portland cement in it at all. We've done it before. We can do it again now. Of course, they had different labor management practices that they could use. And all of this concrete was rammed in place like Frankie piles. So those are the comments I have to get things started, that we have done all of these things. We have been able to construct with materials that are very low carbon. However, the responsibility as to who's responsible when it doesn't set, who's responsible when it doesn't meet the schedule, all of these things need to be worked out before we go to construction. The attorneys will tell you that you can always get it worked out afterwards, but it's a lot simpler to do it beforehand. And I will turn things back to you, Jim.